Now, everything we've looked at is straight line motion so far. Now, in extension 2, we also like to look at circular motion. But just like when we saw projectile motion, and projectile motion wasn't in one direction, we do a similar sort of thing with circular motion where we break it up into horizontal motion. But before we do all that, we need to define a few things, and so let's just do that. Angular velocity. So we've got our circle, and we're travelling around in a circle, certain radius. If I move from A to P, it will sweep out an angle. So rather than thinking about the distance travelled in a certain time, the angular velocity is how much of an angle we sweep out in a certain time period. So that's what we call angular velocity. Symbolised omega is a common one we use, but if we use theta to represent angular displacement, then d theta to t could be angular velocity, or theta with a dot on it would be another way of doing it. And we measure it, as you see, the standard way of measuring it is in radians per second. So omega is d theta to t, or theta dot. Okay, but we can from that work out linear velocity, also known as tangential velocity. So when we're going around in a circle, if we want to work out what the straight line motion is, we assume that the direction we're travelling is at the tangent. Because if you think about going around in a circle, if you were to cut the string, if you like, you would fly off at a tangent at that point. So the direction we're travelling at any instant is in the direction of the tangent at that point. So our P there, about there. And we just give it V for linear velocity. Now, if I let the length of our arc AP be x, so that, if you like, is going to be our displacement, our linear displacement, but we know that the length of that arc is r times theta. So if I differentiate both sides with respect to t, well, r is just a constant, and so I get r times d theta to t, and then we get a very simple formula that the linear velocity, dx to t, is equal to the radius times d theta to t, the angular velocity. And so that's how we can convert. So velocity is radius times, or sorry, linear velocity is radius times angular velocity, or r, or theta dot, if I've got it in my other one. Okay, so period. Well, just like we saw in trig it was 2 pi over n, so we get a very similar expression here, 2 pi over omega. So that's the time taken for one revolution. Okay, let's look at a fairly simple little example. A satellite travelling around the Earth. We know it travels 20 revolutions per day, so it goes around the Earth 20 times in one day. What would that angular velocity be in radians per second? Because as I say, we normally quote in radians per second for our calculations. So if we had to convert this, well, 2 pi radians would be one revolution, and we're doing 20 of those, so I know I'm doing 40 pi radians per day. So divided by 24 and 60, we get pi on 2,160 radians per second. So if you talk about how fast is this thing travelling, that doesn't really tell us that much, because we tend to think of things like kilometres per hour and that to get a feel for how fast it's going. Is that quick or is that slow? Well, it all depends on the radius. So if I want to find this satellite's linear or tangential velocity, the radius, of course, is quite large. It's 9,000 kilometres. So I want it in kilometres per hour. So velocity r times omega, so 9,000 kilometres times pi on 2,160. That would be kilometres per second, though, because remember, I had my angular velocity in radians per second. So to turn it into per hour, now I'll multiply it by 60 and 60. You see, it's travelling pretty quick. 15,000 pi kilometres per hour. That's all I want to talk about to start off with circular motion. So just a couple of basic definitions. 9a and Patel, the odd ones. And then we'll look at the next bit. I guess that'll be Tuesday morning, won't it?